Hello, my lovely Lancers. Today we are going to be learning lesson 14.3 in our acids and bases chapter. First, take note that our brain training number 5, our first one for acids and bases, is due Tuesday, April 28th. I posted it on Saturday, so make sure you go ahead and go do that. It should cover just 14.1 and 14.2, so it doesn't actually cover this lesson. Though anything you do learn in this lesson could actually help with the brain training. Of course, email me if you have any questions on those. But for now, let's move on to 14.3. We're going to learn about pH, and I'm sure you've probably heard that a little bit. We talk about maybe the pH of our blood, pH of orange juice or soda, that kind of thing, as well as if you have a swimming pool, you probably are aware of the pH of a swimming pool has to stay at a specific range. If it gets too high or too low, then either bacteria can grow in it, it gets cloudy, that kind of thing. So we're going to learn about pH and how to actually calculate it. We're also going to learn something called pOH and pKw. So you need your calculator and your periodic table. On your periodic table, I'm going to show you in a second on this slide. I'm going to show you exactly what box we are going to be looking at. So if we move up here, it is this where it says strong acids, the strong bases box, and also our acid base box here, and all of these little pH equations. So I will show you how to use those in our examples. So let's move up back to our slides here. Move that down here. All right, so pH is defined by the negative base 10 logarithm of the concentration of hydronium. If you remember, hydronium is H3O+, also can be written as just H+. Now, before you freak out on me about what the heck is a logarithm, those of you who are not in Algebra 2 yet may not have done these, though I believe it's in Algebra 2 that you learn them. So, I'm going to show you how to do that. It's just a simple button on your calculator. Let's look actually at this next slide. So you can see here's a couple different calculators. Mine is that first one, and you can see it's right next to your 7, and catty corner from that comma, it's right underneath the x squared button. It just says log. Simple as that. That's your log button. So once you locate it, you can press the log button, and it shows you log, and it opens up a parentheses for you. Then you would type in, if you look at your equation, for pH, it is the negative log of H3O concentration. Now, to use the negative sign, don't actually use the minus or subtracting button on your calculator. Use the little negative button. It shows it inside parentheses, and it's next to your enter button and below the number 3 on a TI calculator, a TI 83 or 84. So you would click the negative sign, and then you press the log sign. So your calculator would then look like this. Negative, and it says log, and it opens up a parentheses. Pretty simple as that. You would type in then whatever the concentration of H3O is, close your parentheses, and press enter, and it'll give you the answer for that. So it's as simple as that. You don't need to worry about learning a whole bunch of math for that. You'll be a step ahead when you get to Algebra 2. Oh. Okay, so in our last lesson, we learned that in solutions, our Kw equation is H3O times OH is equal to 1 times 10 to the negative 14. So that's in any solution, whether it's just plain water, or you have a little bit of an acidic solution or basic solution. Your concentration of H3O multiplied by your concentration of OH is equal to 1 times 10 to the negative 14. Whatever those numbers are, they will always equal 1 times 10 to the negative 14 at a specific temperature. All of the problems that we're doing are going to be at that specific temperature. It doesn't even matter what it is. Temperature is not changing here. So in pure water, H3O concentration is equal to your hydroxide, your OH concentration. So let's do a little bit of math here. If we have this H3O times the concentration of OH is equal to 1 times 10 to the negative 14. And in pure water, if these are equal to each other, then that means we could say something like this. H3O is equal to OH, which is then equal to the same variable. So that would mean we have X times X is equal to 1 times 10 to the negative 14. Well, we all know what that means, right? X squared. So in pure water then, if you were to take the square root of your 1 times 10 to the negative 14, that's equal to X, which is equal to H3O. Go ahead and plug that into your calculator here, and you'll realize that it is 1 times 10 to the negative 7 is equal to X, which is equal to H3O in pure water. Now, let's take find the pH of pure water. Remember our equation for pH. Let's move this a little bit more. Our equation of pH, or equation for pH is negative log of the hydronium concentration. Hydronium then in pure water is 1 times 10 to the negative 7. So pH is equal to negative log of 1 times 10 to the negative 7. Close your parentheses, press enter. Go ahead and just practice typing that into your calculator. Make sure you actually have your log button located correctly. Negative log of 1 times 10 to the negative 7, and we have exactly 7. That is why we call the pH of 7, or of water 7, and it's neutral, and it's because of our concentration of H3O in pure water. So when you have all of your pH scales, which I'm sure you've seen before in biology classes, or maybe in middle school, you've seen that 1 through 14 level pH scale. Anything that is lower than 7 is acidic, anything that's higher than 7 is basic, and then 7 is neutral, and that's why we call water neutral. Let's move on. So here's another way to show it in this little box here. Anything that is acidic is going to have a greater concentration of H3O than you have of hydroxide. So it's heavy on the H3O and low on the OH. Your pH is then going to come out to less than 7. Because if you have a higher concentration or higher number of this, taking the negative log of it is going to get you a lower number. So that's why less than 7 is acidic. For basic, you're going to have a lower concentration of H3O than you do of hydroxide. And you still take the negative log of your H3O in your basic solution. So if you have a lower number here, taking the negative log of it is going to get you a number greater than 7. So that's a quick, easy little chart there to look at. You also have it on your periodic table. It shows the little arrows with the pH scale and 0 through 14, where it says 7 is neutral. It tells you acidic on the lower number side and basic on the higher number side. So you don't even have to memorize that, which I imagine you already do, just because it's a common concept. All right, so let's look at this. Here's a whole scale of different pH numbers. First, just look at your hydrogen concentration, where you have your H plus and all of those values, and then your pH. Don't worry about the pOH or OH just yet. We'll get to that. So if you start out and look at that, stomach acid has a hydrogen or hydrogen ion, H3O concentration of 1 times 10 to the negative 1. It looks like it's maybe slightly lower than that. And if you take the negative log of that, that gets you 1. So your stomach acid is around a pH of 1. That's what we need it to be in order to digest all of our food. It needs to be really, really strong. Lemon juice, of course, is a little bit less than that, but still it's around a pH of 2. Cola, really any soda, has a pH between 2 and 3. And then, of course, you go all the way down there, wine, tomatoes, black coffee, rain, saliva, and milk. And I think that's an interesting note there. Milk is actually slightly acidic. It's a little bit less than 7. And we think of it as being alkaline or basic, but it's actually much closer to neutral than anything else. On the other side of your basic side there, you've got human blood is just slightly basic. So it's actually about 7.4 your blood is. And then you have seawater, borax, lime water, and then notice your household ammonia and bleach. Those are cleaning detergents and cleaning agents. And those are very, very basic. Basic solutions are just as dangerous as acidic solutions. So if you think about someone getting an acid burn, that feels, or that sounds pretty awful, right? It's going to burn your skin. We call it a burn because it feels like it's burning your skin. Where a basic burn actually does more damage because you don't feel it right away. You could spill some strong base on your skin and it's going to be instantly doing damage, but it doesn't burn the way an acid does. So you don't think about it. You don't think about washing it off right away. You maybe didn't even notice you spilled some on there, and it ends up doing more damage because it's on your skin longer. So actually basic compounds and solutions are more dangerous than acidic if we're comparing the same level of concentration. All right. So we have actually different P scales. The P in pH just means to take the negative log of it, the negative base 10 logarithm of that quantity. So for pH, that would mean hydrogen ion or your hydronium. But you could take the negative log of hydroxide, your OH, and that would be calculating pOH. You could take the negative log of your Kw, which that is your Kw value. Take the negative log of that, and that's your pKw. So the lowercase p, it's always lowercase in pH and pOH. That p means take the negative log of the following compound, whatever it is. So we're going to do some examples of this. Quick little note on hydrogen. If you remember, hydronium is H3O. And that can be written as H plus or H3O plus. Either way, they're completely interchangeable. When you write H3O, you're just writing the hydrogen ion with it attached to water. If you remember, H3O just comes from water with your extra hydrogen ion. So we can write it interchangeably, which means in our pH equation, when we say pH is equal to the negative log of hydrogen ions, you could also write it as pH is equal to the negative log of H3O. These are going to be the exact same value in any one given solution. Completely interchangeable. All right, so let's do a couple of examples. I will make this larger so we can see my work here. So for the first one, if a solution has a hydrogen ion concentration of 1.5 times 10 to the negative 6, what is the pH of the solution, and is this solution basic or acidic? So let's go ahead and write out our equation like I put on the slide there. pH is equal to negative log of H3O. It's telling us that H3O is 1.5 times 10 to the negative 6. So to find the pH of that, we would take the negative log of 1.5 times 10 to the negative 6. Close your parentheses and press enter. So go ahead and try that with me, making sure you are getting your calculator syntax correctly. Times 10 to the negative 6. We have 5.82. For significant figures and for pH, it's a little bit different. You look at the number of sig figs that's given in the number. So when you have an exponential number here, you just look at the decimal. You don't look at this. This does not count for significant figures, just these. So we have 2 sig figs, right? 1, 2. Now for pH, to carry the same level of significant figures, however many sig figs you had, that's how many decimal places you have to have over here. So the 5 isn't counted when we're counting how many sig figs. So we need 1, 2, we need 2 decimal places here. So that's how that works. All right, so that's your answer to the first one. Now, is it acidic or is it basic? So then you have to look at your chart. And if you don't already have it memorized, that anything less than 7 is acidic, you could find it right there. So this is acidic. Done. All right, let's do the second problem. I will move the video. All right. If you want, go ahead and pause and see if you can try this on your own. All right, so pOH is equal to the negative log of hydroxide. If a solution has a hydroxide concentration of 8.5 times 10 to the negative 2, what is the pOH of the solution? Is this basic or acidic? According to our equation, we just need to define the pOH. We need to take the negative log of 8.5 times 10 to the negative 2. Plug that into your calculator. Make sure you have everything written out correctly. 8.5 times 10 to the negative 2. And I have 1.07. Again, we've got two significant figures, so then we need two decimal places for the pH. So there's pOH. Follows the same sig fig rules as pH. Now the question says, is this basic or acidic? Now the periodic table just gives you your pOH scale. It doesn't give you it gives you the pH scale, not the pOH scale. So we need to convert this. pH is defined by the negative log of hydronium. Well, how do we find hydronium from hydroxide? Do you remember your kW equation? Let's write that out. 1 times 10 to the negative 14 is equal to H3O times hydroxide. So if you divide both sides by hydroxide, that's going to equal H3O. Well, hydroxide from the problem is 8.5. So let's go ahead and do that. Here's where parentheses are really, really important. Plug those in. So we have 1 times 10 to the negative 14 divided by parentheses 8.5 times 10 to the negative 2, close your parentheses, and our hydronium, the H3O, is then equal to 1.176, let's preserve a few sig figs here, times 10 to the negative 13. Let's move that over a little bit. Okay, so there's your hydrogen ion, and then you can take the negative log of that to actually find the pH so that you could then read your pH scale. So let's go ahead and do that. We have, I'll put it up here, negative log of hydronium, 1.1765. What do we have then? Negative log 1.1765 times 10 to the negative 13. Now we still, this is not accurate sig figs, we're just using more so that we can preserve the accuracy of our significant figures. We still only have, according to here, two significant figures. So let's write out our pH. We need two decimal places for the two sig figs. So there's your pH, and this one was our pOH. Now we can see if the pH is 12.93, look on your chart, and that is a basic solution. So that's how you figure that out. Now that was slightly complicated. I'm going to show you an easier way of doing that. First, let's go to the next slide. What do we have? Yes. So I'm going to actually show you some really cool math with this. Tiny little math lesson. For those of you who are in Algebra 2, often by the time I get to acids and bases in the end of this second semester, usually Algebra 2 classes have gotten to logarithms already, so this might be a repeat of something recent you just did. And if you haven't gotten to Algebra 2 yet, you're going to be a step ahead here. So I'm actually going to make my video larger so you can see this better. So to start with, we have our lovely equation here. Hydroxide times hydronium is equal to Kw, which is equal to 1 times 10 to the negative 14. So I'm going to write that out here as well. I'm keeping these up here for a reason. We'll get to them in a second. That's equal to Kw, which is equal to 1 times 10 to the negative 14. And that is all on your periodic table. It's one of your equations there. Now, if we're going to, if you remember in algebra, you can take, you can do the same thing to both sides of the equation. It's not changing the value of the equation. If you're going to add 2 to this side, you have to add 2 to this side. Nothing's actually changed. You could multiply 2 or 3 to both sides of the equation. Nothing's changed. So that's what we're going to do. We're going to take the negative log of both sides of the equation, or in this case, all of the parts of our equation. So we're going to do this in a second, but first let's take the negative log of Kw. So we'd say negative log Kw. That's for this little section here. We also then have negative log of 1 times 10 to the negative 14. And I'm doing good here. Not falling off yet. All right. So when we take the negative log of this section over here, this is the same thing as saying taking the negative log of hydronium, then plus take the negative log of hydroxide. That's the way logarithms work. Your multiplications then turn into addition. Don't ask why, you can ask your math teacher why. Negative log of hydronium, and then plus, we're going to put this in parentheses so we don't get mixed up with our negative sign, negative log of hydroxide. So now we've taken the negative log of this side, of this, and of this. Now let's go back up here. So look at this right here, negative log of H3O, that's equal to pH. So we can substitute and say pH plus, well, what is this equal to? Negative log of hydroxide, same thing, right? That's equal to pOH. So we say pH plus pOH is equal to negative log of Kw. If you remember, P is just equal to negative log. So this is actually Kw. Negative log of 1 times 10 to the negative 14. Well, let's do that on our calculator here. Negative log of 1 times 10 to the negative 14 gives us 14. All right, so even if this math did not make sense to you, don't worry. This is the important part right here. pH plus pOH is equal to 14. This is true for all solutions there. It's the important part of all of this little math lesson. So let's move on here. By the way, this is on your periodic table. You can locate it on your acids and bases box right there. All right, what do we have next here? Oh yeah. So we're gonna get rid of this part and this part. And this. So like we have this, pH is equal to negative log of H3O. Well, what if a problem gave you the pH and you needed to find H3O? Well, you know how division is in a sense the opposite or the backwards of multiplication, and addition is the opposite or backwards of subtraction. For negative log, you have to raise the power by 10. That's the opposite operation here. So if we want to find H3O, let's start with that equation. You know what, I've already got it written, so let's go like this, so I have more room. We're going to raise both sides to the power of 10. So we're going to say 10, oh, that's a negative sign, so let's actually move this over. Algebra, right? Multiplying both sides by -1 moves the negative sign over here. So let's raise this side by the power of 10. So we have 10 to the negative pH is equal to 10 to the log of H3O. Right? Follow? Raising this side to 10, or to the power of 10, raising that to the power of 10. 10, and then the log, those are backwards. That's like saying multiply by 10, divide by 10. It doesn't change it, right? So this literally goes away. And then we're left with just H3O. So again, don't worry about the math. If that was too confusing and you don't understand it, don't worry about it. You'll get to it in algebra too. But you have this equation on your periodic table. 10 to the negative pH is equal to H3O. So then it follows that 10 to the negative pOH is equal to hydroxide. That way, if you are given, let's move this back over. If you're given H3O and you need to find pH, use this equation. If you're given the pH and you need to find H3O, use this equation. Same with the pOH. Those go back and forth that way. All right, so we're going to do some practice problems with these. Actually, let's put that back out here. Okay. So if a solution has a pH of 5.63, find the H3O. So if the solution has a pH of 5.63, plug it into this equation. So we'd say 10 to the negative 5.63, that's going to be equal to H3O. Okay? 10 to the power of negative 5.63. And I have, that is equal to 2.3 times 10 to the negative 6. Now, how do I know to round it there? Well, pH has 2 decimal places here in this. That means my end answer needs to have 2 total significant figures. So there I have 1, 2, and that would be doing the sig figs correctly there. So there's your first example. Next one. What is the pH of a solution with H3O of 5.63 times 10 to the negative 4? Well, now since we are given our H3O and we're asked for pH, plug it into this equation. So you have negative log, I'll write it out, negative log of 5.63 times 10 to the negative 4. I really encourage you to practice all of these calculator problems with me because you want to make sure that you actually are getting the calculator buttons typed correctly, because you don't want to have to go through all of the difficult chemistry concepts and then only to get it wrong because you didn't know how to use your calculator. Don't let your calculator be smarter than you. Okay, so that is equal to, we have 3.25. 3.25. We have actually 3 significant figures here, if you notice, so then we need 3 decimals. So I take that back. We're going to go, not going to round it, and we're going to say, we're going to write that, 3.249, because the next number is a 4, and that would not round that number up. Okay, so there's your answer to the second example. Next one, if the pOH of a solution is 3.49, what is the pH? This is the easiest one by far, because look at your equation. We have pH plus pOH is equal to 14. So you just subtract from 14, essentially. pH plus pOH is equal to 14, and it says that if the pOH of a solution is 3.4, so we have pH plus 3.49 is equal to 14. Well, how do we find pH? 14 minus 3.49 is equal to pH. Plug that into your calculator. 10.51. So that makes it much easier without having to use your kW equation and backtracking and finding your hydroxide and hydronium equations, then going back to pH. Just use this equation. If you're given either pOH or pH, you can find the other one very easily by just subtracting from 14. All right. Oops. All right. What are the 7 strong acids? So if you look on your periodic table, you have a list right underneath your acid-base box. You have a list that says strong acids, and it's listing all 7 of them there. Don't need to memorize them, you're good. These are, by definition, strong electrolytes, which means they're going to completely dissociate. They're going to separate in solution. They're not going to exist as your hydrogen, and look at that first one, hydrogen and sulfate. The hydrogen are going to split away from the sulfate, which means then, if they exist solely as ions in solution, according to your dissociation reactions, however much your concentration of the strong acid is, that's the exact same concentration of H3O, and that's important for finding pH. You have to have the H3O to find pH. So you can see that on there. I put strong acid in brackets, so the concentration of your strong acid is equal to the concentration of H3O. And we'll do a few examples to illustrate that. Strong bases are similar. Your strong base concentration is going to be equal to your hydroxide concentration, and that is in your little strong base box that's right next to your acid base box. So it says group 1A and group 2A. On the periodic table, your group 1A is your first column here, and those are your alkali metals. And then group 2A is the second column. Those are your alkaline earth metals. And so it says group 1A and 2A hydroxides, except for beryllium and magnesium, which is the same way as saying the heavier group 2A or alkaline earth metals, calcium, strontium, and barium, with hydroxide, those are your strong bases. They're going to completely dissociate and exist solely as ions in your aqueous solution. So for strong bases that only have one hydroxide, which would be with your first column, then the concentration of your strong base is equal to the concentration of hydroxide. And again, we're going to do examples of that. All right, so find the pH of a 0.05 molarity solution of HCl. Well, in order to find the pH, we need H3O. How do we find H3O from HCl? Well, is it a strong acid? Look down on there. Hydrochloric acid is HCl. Therefore, it is a strong acid. So because the concentration of the strong acid is equal to H3O, 0.05 then is equal to H3O. So we just take negative log of 0.05, and that's going to be equal to the pH of this solution. Negative log 0.05 is equal to 1.3. We have two significant figures, therefore we need two decimal places. 1.30 is your pH of this solution. Done. All right, let's go to the next one. Find the pH of a 0.1 molarity solution of NaOH. Well, sodium hydroxide. In order to find the pH, you need H3O, but we're given a base. So if we wanted, we could go straight to using our Kw equation and find hydroxide, or from hydroxide, find your hydronium. Or if we find the pOH of this solution, we would then just subtract from 14. So that's an easier, simpler way. Let's try that first. First, understand that sodium hydroxide, NaOH, is a group 1 hydroxide, which means it's a strong base. So whatever concentration of sodium hydroxide, that's the concentration of hydroxide that you have. So 0.10 is equal to hydroxide. If we take the negative log of hydroxide, that's going to be equal to pOH. So let's do that. Negative log of 0.1, it's 1. Okay, pH plus pOH is equal to 14. Therefore, 14 minus 1 from your pH is equal to pH, which is 13. So that's the answer to example 2. The pH of a sodium hydroxide solution is going to be equal to 13, and that makes sense. If you have a strong base, of course, you're going to have a very high basic pH. There's your reasonable check. All right, next one. Last one, actually. Find the pH of a 0.1 molarity solution of calcium hydroxide. There's an extra step to this. Calcium hydroxide is a strong base. But notice in your compound, you have 2 hydroxides. So when we write out our dissociation reaction here, we're going to have calcium 2 plus. It's going to dissociate into calcium with its 2 plus charge and 2 hydroxides. From here, we needed 2 in order to make this a neutral compound. So for every one of these, look at our ratio, 1 to 1 to 2. For every one of these, we have twice as much hydroxide. So since we have a molarity of 0.1 calcium hydroxide, we'd have 0.2 molarity hydroxide. That's just the next step that you have to use when you have a base with 2 hydroxides. Then we can follow the same procedure that we did from the previous problem. Negative log of your hydroxide is equal to pOH. Let's find that. Negative log of 0.2 is equal to 0.69897. This is one, no, we've got technically 2 sig figs. So we've got 2 sig figs here, which means we only need 2 decimals for pOH, but we're going to preserve a few more for when we're finding pH, because we're not done yet. So 14 minus the pOH, 0.69897, subtract that from 14, and we have 13.301. We want 2 sig figs, so 2 decimals. So there's your pH. And again, that would make sense. You have a strong base, calcium hydroxide, and so your pH should be very high basic pH. All right, that is the last problem that we have. So go ahead and start working on 14.3 and email me any questions. I will also work on doing some live tutoring sessions as well this week. I think you should take advantage of that.